So let us now discuss about one more very important concept called as the line integrals in case of vector fields. And once we understand this concept of line integrals, we can use this in the study of one more very important concept called as curl of vector fields. Now to understand the philosophy behind these line integrals, let me take one example. Now that is nothing but we are having some force field in a particular direction. Now whenever we say force, does it have some magnitude? Yes. And is it also having some direction? Yes. So because of that, we can represent this by means of some vector, and that vector is f bar, and f bar is nothing but we can write this as f naught f cap, and whatever is the force we have taken, that is a constant force. That is nothing but at every point in space the magnitude of force remains exactly the same. And what about the direction? The direction is oriented along a particular direction. And given this force field, we want to move a body from where to where? From one point to the other point. Let me call this point as I and this as F. And we are moving from I to F along a straight line. And let us say that line corresponds to this path. Okay. Now the length of this distance is nothing but from initial point to the final point. That length corresponds to L. This length corresponds to L. And does it also have a specific direction? Yes. Whenever we are going from I to F, we are having some specific direction, that is nothing but this direction. So can you express this path as a vector? Yes, we can express that path as this is L bar is equal to magnitude of length as well as the unit vector along this direction. And let me call the unit vector along the direction as nothing but that is L cap. Okay, so we are having also a vector representation of the path. And I want to find out how much is the work done. How much is the work done? Work done in moving a body. In moving a body from where to where? From the initial point I to the final point F. Okay. And whenever we are going from initial point to the final point, we are taking what path? Along L bar. We are taking the path which is nothing but L bar path. Okay. And that too, this body is moved in what force field now? In a force field. In a force field F bar. Okay. So in such cases what we will do is, now we know one very simple concept. Whenever we are moving a body perpendicular to the force, in that case, do we have to spend any amount of energy? No. Only whenever we are moving a body along a direction of force or opposite to the direction of force, in that case only we are supposed to spend some amount of energy. Okay. Now in this case, if at all you split this F bar into two components, one component of F bar in the direction of this path, and one more component of F bar perpendicular to the path. In that case, we are having two components of F bar. And what can you call about this component now? I will call this component as Ft, which is tangential to this particular path, and one more component is nothing but Fn. So because of that, we can write the vector F bar as nothing but what? F bar is equal to, this is Ft, and in what direction? In the direction of L cap. Ft, L cap in the direction of the path, and one more component is Fn, n cap. Let us say perpendicular to this L cap, we have one more unit vector which is nothing but n cap. So because of that, whatever is a unit vector in this direction we have, that is being called as n cap. In such a way, the angle here is nothing but 90 degrees. Okay. Now given this F bar, please tell me how much amount of work we are supposed to do. Now in this case, are we moving in the direction of force or in the opposite direction of force? Obviously, if you look at, we are moving from I to F and we are having the component of force which is nothing but Ft in the direction of the path that we have taken. So because of that, we are moving the body in the direction of force, and whenever you are moving a body in the direction of force, the work done is positive or negative? Work done would be positive whenever we are moving the body opposite to the direction of force. But in the present case, we are moving the body in the direction of force. So because of that, whatever is the work done that we have, we know that work done is equal to what? This is force times the distance the body has been moved. Okay. Now in this case the force is constant. So since the force is constant, now our task becomes very simple. But which force are we supposed to consider? We are supposed to consider the force which is along the direction of path. And along the direction of path, the force is nothing but Ft. So because of that, here whatever is the force we have taken, that force corresponds to, this is Ft. Okay. And into the distance, how much is the distance that we have moved? The distance that we have moved along the path is nothing but L. Okay. And furthermore, if you notice, whatever is the work done, will that be negative or positive? Obviously that will be negative, because are we moving the body in the direction of force or in the opposite direction of force? Obviously in the along the direction of force. Okay. So because if you look at here, what we are doing is we are simply multiplying two terms. One term is nothing but the component of vector. The component of vector along what direction? Along the direction of the path, and we are calling that as Ft. And one more component is nothing but the length of the path. Okay. And how can you express this term now? That is nothing but Ft into L. How can you write that now? We can write it as simply this is nothing but minus of F bar dot L bar. Okay. F bar dot L bar. Because whenever you take F bar dot L bar, what do you get now? F bar is nothing but this term. So I can write this as Ft L cap plus Fn N cap. Okay. Dot L bar we are having. What is L bar? L bar is nothing but the magnitude is nothing but L in the direction of L cap. And what is the angle between N cap as well as L cap? The angle between N cap as well as L cap, both are nothing but 90 degrees. So because of that, the dot product of them becomes equal to 0. And what about L cap dot L cap now? L cap dot L cap is nothing but 1. So because of that, this finally boils down to Ft into L. And that is what we have here. So whatever is the magnitude which is called as Ft into L has been written as F bar dot L bar. Now we could write this because now in the entire region of space, the magnitude of force is constant. But what if the magnitude of force is a function of space parameters itself? That is, at various locations in space, the magnitude of F itself changes. In that case, how do you calculate the total work that has been done? Now in the second case, what we are assuming is, we are taking this force is a function of now space parameters. That is, the magnitude of force changes with respect to various points in space. Let us say now this force is a function of XYZ parameters. So because of that, at various locations in space, the magnitude of force will definitely change for us. Okay. Now in this case, how do you calculate the total work done in moving the body from the initial point to the final point? Now for that, what we will do is, we will simply take a very small section of this path. Now in this path, from the initial to the final point, we are considering a very small path, and that small path has what magnitude now? The length of this small path is nothing but this is dl, and having what direction now? Having the same direction, which is nothing but L cap. So because of that, now what we will do is, instead of taking the entire distance, we are taking only a part of the length of this path. Okay. And in that process, what do we obtain? We obtain only a small magnitude of work that has been done. And that would be equal to what? That would be equal to the force into the distance. Okay. And which force you are supposed to consider here? The force which is in the direction of the path. That is nothing but Ft. But whenever I say the magnitude of force is a function of XYZ, what about this Ft? Now this Ft is also a function of XYZ parameters. This is also a function of XYZ parameters. Okay. But now, how much is the distance you have moved? The distance we have moved this particular body is nothing but only a distance of dl. Only a distance of dl. That is, we are calculating how much is the work done in moving the body from this location to this location, only for this much amount of distance, but in this orientation. Okay. And that is what we will get now. But how can you express the same thing in terms of a vector? We can express the same thing in terms of vector. Here we will have dl as nothing but F bar dot dl bar. This is what? This is the infinitesimally small work that has been done. Work that has been done. Now if at all I want to find out the total work, how much is the total work that has been done now? Work is equal to integral of dw. From where to where? in moving the body from initial point to the final point. Okay, and because of that we can write this as this is minus of whatever is the expression we have, that is nothing but F bar dot dl bar, and we are integrating this from where to where? From the initial point to the final point. And whatever is the integration we have here, now this integration corresponds to the line integral. So this integration corresponds to the line integral, okay, wherein we are multiplying a vector with a particular length. In what direction we are considering this vector now? In the direction of the path of the length is where we are multiplying this particular vector as well as the small differential length, and then integrating from where to where? From the initial point to the final point. Now in order to solve such kind of questions, we have to understand the concept of line integrals, okay. So let us now understand what are the different types of line integrals we have in the vector fields, okay. So let us say we are having some randomly oriented vector, and that randomly oriented vector is nothing but this vector, some randomly oriented vector we have taken A bar. And apart from this randomly oriented vector, we have also taken some randomly oriented path, and let us say that randomly oriented path is nothing but this particular path. And in this path, this is the initial point as well as this is the final point. And can I call this as a line or a curve? Obviously, this path corresponds to some curve, okay. So using the term called as line integral is actually a misnomer. We can call them as curve integrals or also path integrals, okay. Now I want to find out what is the line integral of A bar along this particular path, okay. And for that what we will do is, we will divide this particular path into smaller components, and let us say this is the first section, this is the second section, this is the third section, fourth section, fifth section, sixth section, 7, 8, 9, let us say 10. We overall have divided this entire path into some 10 paths, okay. And let me call this path as nothing but this path corresponds to, this is DL1, L1 cap, and the second path we have, this is the second path, and we can call this second path as nothing but this is DL2, L2 cap, and the third path as nothing but this is the third path we have considered. So this is nothing but this is DL3 into L3 cap, and this is the fourth path. The fourth path corresponds to DL4. This is DL4. Now L4 cap, and so on, okay. So by dividing this curve into many smaller paths, what we have done is, we have converted each of the section of this curve into a small line. So because of that, whatever is this path integral we have divided this into many smaller line integrals. So because of that, please tell me, in this particular path, what is the product of A bar component along the direction of L1 cap multiplied with this particular length, which is nothing but DL1. I can write that as, that is nothing but A bar dot what? This is nothing but DL1 bar. So this is a very small line integral we have obtained. Now in this small section of the path, now in the second section of the path, what is the line integral? The line integral corresponds to, this is nothing but plus A bar dot, now this is DL2 bar, because obviously DL2 bar is oriented along a different direction as compared to DL1 bar. And what is the line integral along the direction of L3 cap now? That is nothing but A bar dot, this is DL3 bar. Now and so on. Finally what do we have? Plus we are having A bar dot, this is nothing but DL10 bar. Now in all these cases, whenever we take a dot product of A bar with respect to DL1 bar, what we are doing now? We are simply multiplying the component of A bar along the direction of L1 cap multiplied with the length of the first vector, which is nothing but DL1 bar. And that is what we are doing. So finally this will give us what now? This will give us the value of A bar dot L bar. And what is this L bar ultimately? This L bar corresponds to the path defined by this particular red curve that we have taken earlier, okay. Now this L bar is nothing but some randomly oriented curve. Now we have performed the line integration along this particular curve by dividing this entire curve into smaller lines. Because any curve, whenever we are taking a very small section of that curve, approximates to a line. So because of that, we have converted the curve integral or path integral into many smaller line integrals. Okay. Now finally, what's the answer now? I can write this as this is summation of, this is sigma, now n equal to 1 to 10, and we have taken a bar dot dl bar I. Okay. And whenever n tends to infinity, in that case what happens? This summation becomes equal to integration. Integration of what? Integration of a bar dot dl bar. And obviously even dl bar is nothing but some mathematical equation. And a bar anyway is nothing but some vector field defined by means of some mathematical expression. Apart from that, we are also defining the dl bar by means of some mathematical expression. Okay. And this integration is being performed over what? Over a particular path, and let me call that path as nothing but L. Okay. So finally, this is expression of the line integration of a bar along a particular path which is nothing but L. Okay. Now if at all you look at this particular curve that we have taken, is it open curve or closed curve? Obviously this is open curve. What is an open curve? Whenever the final point as well as initial point both are not same, in that case we are calling that curve as the open curve. And whenever the final as well as initial points both are same, in that case that curve corresponds to a closed curve. Okay. So because of that, whenever we are taking the line integral of what? Of a bar vector along what path? Along the path L. Along the path L. Please understand, this path L will have some direction. Okay. And we can express that quantity as nothing but what? That quantity as nothing but this expression. And in this case, L is open path or closed path? Obviously L bar corresponds to, this is open path. Okay. And let us say we are performing the line integral of a bar along one particular path, and let me call that path as nothing but L, but rather that path is nothing but closed path. In that case, what is the expression of integration now? We will show it by means of a contour. Okay. And this integration is being performed over one length, and that length is nothing but some vector, and this is a bar dot dl bar ultimately. Now in this case, whenever you show a circle here, that is nothing but a contour here. Now in that case, whatever is the path we have taken, that path L bar corresponds to a closed path. Okay. Again, just to show you one example here, let us assume that we are having some randomly oriented vector, again like in the previous case a bar. Now we want to take a line integral of this particular a bar in this particular direction. Okay. Again, we are starting from, let us say, this point and again coming back to the same point. Now in this case, what we are supposed to do? We are supposed to take a closed integration. Okay. Now whenever we have a closed integration, can we not split this into two path integrals now? Yes. Let us say this is the initial point, this is the intermediary point, and again this is the final point we have. Okay. So because of that, what we will do is, we will take this as nothing but L1 and this path as nothing but what? This is L2. Okay. So because of that, whenever we are having a closed integral, we can write this closed integral into two or more than two open integrals. Okay. So because of that, we can write this as, this is open integral of a bar dot dl bar along what path? Along the path L1 plus we are having integral of a bar dot dl bar along the path L2. Here if you notice, I didn't show any circles. What does it mean? The path L1 as well as the path L2 both are nothing but the open paths. Whenever you consider only L1, can I say that this is nothing but the path L1? We are going from this point to this point. Now in this case, the initial point as well as the final point, are they same? No. So because of that, now the path L1 is nothing but one open integral or open path. And what about only whenever you take L2 now? That is nothing but this initial point to this final point for L2. Is it also one more open path? Yes. So because of that, individually L1 as well as L2 both become what? Both are two open paths. Okay. Now let us look at one example to understand the concept of line integrals. And we have a vector field which is a bar is equal to x square x cap plus y square y cap. Now find the line integral of h bar dot dl bar taken along a particular path. Now if you notice, do we have a circle here? No. So because of that, whatever is the integration we have here, is this open integral or closed integral? Obviously this is nothing but open line integral. This is open line integral. And the path L is defined by the curve which is y equal to x square from where to where? From 0, 0 to 1, 1. So first of all, let us take the path. The path is along what curve now? The path is along the curve which is nothing but y equal to x square. So because of that, the path of integration is along the curve which is nothing but y equal to x square. From where to where? From 0, 0 to 1, 1. Okay. And what is the differential length we'll take? The differential length vector. Now in case of Cartesian system, if at all you look at the given vector field that is given in terms of Cartesian system, in the Cartesian system the differential length vector is nothing but dx x cap plus dy y cap. We don't even have to take the z component. Okay. Now here we are having two variables. Let us convert both the variables into one single variable. And for that what we will do is we will differentiate this function with respect to x. And whenever you differentiate this function y with respect to x, what do you get? This is dy by dx becomes equal to what? This is equal to 2x. So from this, can we write dy is equal to what? From this, dy is equal to 2x dx. Okay. So we can write this particular vector as nothing but what? This is equal to dx x cap plus what is dy? Dy can be written as this is 2x dx x cap. So this is what we have regarding what? Regarding the differential length vector for us. Okay. Now because of that we can find out what is the value of h bar dot dl bar, and that would become equal to what? That would become equal to we have x square x cap plus y square y cap and dot producted with that particular vector which is nothing but dx x cap plus we have 2x dx y cap. Okay. And whenever you take the dot product, in that case what will happen? Now the x components will be multiplied as well as the y components are multiplied, and we have to add both of them. And in that case what do you get now? This becomes equal to integral of x square into dx. The first term is x square into dx. The second term is what? This is y square into 2x dx. So because of that we can write this as plus 2x y square into dx. Okay. So this is what we have. And furthermore we can replace this y square also by means of this expression. Now according to this, what is the value of y? Y is nothing but x square. So because of that I can replace this as this becomes equal to x square plus 2 into x into y square. Y square becomes how much? That is nothing but x power 4. So because of that x power 4 into x becomes x power 5. So this is 2x power 5 into dx. Now in this integration the only unknown value is nothing but what? That is nothing but x, and x varies from where to where? X varies from 0 to 1. Okay. So because of that substitute the limits to be equal to 0 to 1. What do we get now? Integral of x square is nothing but this is x cube by 3 plus the integral of x power 5 is what? This is 2 into x power 6 by 6, and we can integrate this from 1 to 0. So whenever you substitute 0 that result becomes equal to 0, and whenever you substitute 1 what do we get now? That is nothing but 1 by 3 plus 2 by 6. 1 by 3 plus 2 by 6 becomes equal to what? That is nothing but 2 by 3, which is this can be written as 0.667. Okay. In fact this is one of the questions that has been asked in GATE 2020. So this is one of the questions that has been asked in GATE 2020 electrical paper, and moreover this is the exact same question on the back side, exercise questions of SADICO. Okay, you can cross verify this. This is one of the exercise questions of SADICO. Exact same question with the exact same answer has been asked in GATE 2020. Okay. So let us look at one more example. Here we have been given a vector field which is f bar is equal to rho square rho cap plus z phi cap plus cos phi z cap. Now given this vector field we have to find out the line integral of f bar dot dl bar, where L is nothing but apart from the point 2 comma 0 degrees comma 0 to 2 comma pi by 4 comma 3. And what is the path that we are following from the initial point to the final point? Now L corresponds to the path. First of all we are having an arc wherein the value of rho remains constant to be equal to 2, And what about the phi now? Phi changes. In the first path, only the phi changes for us, okay? And the value of z also remains constant. And after you change the value of phi only, what we are doing is we are changing the value of z. If you look at between the initial point as well as the final point, the value of rho remains constant. The value of rho remains constant, but rather the value of phi changes as well as the value of z changes from 0 to 3. But rather we are making those changes part by part. In the first part of the curve, we are making only the changes with respect to the phi, and in the second part of the curve, we are making changes only with respect to the z. So because of that, along this path where the value of phi changes, please tell me what is dl bar. Now along this direction, the value of dl bar becomes simply equal to, this is rho d phi along the direction of phi cap, because that is where we are having the change. Now along the direction of phi cap where we are having the path now, please tell me what is the differential length. Now the differential length corresponds to rho d phi into phi cap. Now what about this direction now? Now in this particular path, the only parameter that changes is nothing but z. So because of that, along this path, we can write this as, this is nothing but dl bar is equal to dz z cap, okay? In general, we know that the differential length vector in case of the cylindrical coordinate system is nothing but d rho cap plus rho d phi cap plus dz z cap. This is the in general differential length vector in the cylindrical coordinate system. Now in the first path, the only parameter that is changing is nothing but phi. So because of that, as differential length vector, we have taken only this component. In the second path, the only parameter that is changing is nothing but z. So because of that, dz z cap is what we have taken as a differential length vector in the second case. Now ultimately in the given case, we are supposed to calculate what is the value of f bar dot dl bar along what? Along a particular path called as L. And we can write this as what? This can be written as two line integrals, okay? And let me call this as L1 and this as L2. And in both the cases, we are having f bar dot dl bar, and here also we are having f bar dot dl bar. But the dl bars in both the cases have been changed for us, okay? And what about L1? L1 corresponds to this path. We can call this as L1, and we can call this path as nothing but L2, okay? So because of that, here if you notice, what is f bar dot dl bar now? We can call this as the first differential length vector in the first path now. So because of that, we can write this expression as, now what is f bar dot dl bar? Now there we have only the phi component. So let us take only the phi component here also. Here the phi component is nothing but z. Z into there we have rho d phi, okay? Now along this path, the only variable that is changing is nothing but phi for us. And phi changes from where to where? Phi changes from 0 to pi by 4, okay? And furthermore, along this path, what is the value of z? The value of z becomes equal to 0. And what is the value of rho? The value of rho is nothing but 2. So 0 into 2 into d phi becomes obviously equal to what? This is nothing but 0, okay? So along the first path, the integration has become equal to 0 for us. And what about along the second path now? Along the second path, we are having now f bar dot dl bar. And f bar dot dl bar and dl bar, if you notice, has only the z cap component, and the z cap component here is nothing but cos phi. So we can write this as cos phi into dz. And along this path, the only variable we have is nothing but z. So let us write the limits of only z, and z changes from where to where? This is changing from 0 to 3 for us, okay? And what about the value of phi along this particular path? Along this path, the value of phi becomes equal to pi by 4, which is nothing but what? 45 degrees. And what is cos 45? That is nothing but 1 by root 2. And what is integral of dz now? The integral of dz is nothing but z. And z by root 2 is what we can take. And the root 2 is because of the cos 45. And for z, what are the limits now? This is from 0 to 3. Okay. So because of that, whenever you substitute the limits, the answer that you get is nothing but 3 by root 2. Okay. So this is how you perform the line integration in the given case where we are not just having one path, but rather we are having two paths being specified here. Okay. So let us look at one more question. Find the circulation of the vector b bar is equal to xy x cap minus yz y cap plus xz z cap around the path L on the x equal to 1 plane shown below. And whatever is the plane given to us, this is nothing but x equal to 1 plane where the value of x remains constant. So since the value of x remains constant in this entire plane here, what we can do is we can substitute the value of x to be equal to 1. and whenever you substitute the value of x to be equal to 1, we can rewrite this vector field as nothing but what? This is b bar is equal to 1 into y cap, 1 into y x cap, which is nothing but y x cap, minus we are having y z y cap, plus here we are having z z cap. Okay, so this is what is the new vector field that we have, substituting the value of x to be equal to what? The value of x to be equal to 1. Okay, now here we are having a closed path. If you notice, here we are having a closed path. If I assume that this is the initial point as well as this is also the final point for us. Okay, we can split this path into 3 parts. The first part is nothing but, we will call this part of the path as nothing but L1, and this is L2, and this is L3. Okay, and how can you write L1 as? I can write L1 path as nothing but L1 bar is equal to how much? Now this is in what direction? This is in the direction of y. So because of that, in the direction of y, what is the differential length now? That is dy y cap. Okay, and what about this path now? This path can be taken as, this is L2 bar. If you notice, this is along the direction of increasing z. So because of that, we can write this as, this is dz z cap. Okay, now in the last case, we are having this particular path now. Now first of all, please tell me what is the equation of this path. Now here, if you notice, the slope is nothing but 1, because the value of x as well as, y as well as z both are nothing but 1. So because of that, we can write this particular line equation as, this line equation to be equal to, we can write this as z equal to y. So because of that, can we write the value of dz to be equal to dy? Yes, we can write it as dz to be equal to dy. So along this particular path, we can write the path equation as nothing but, this is dy y cap plus dz z cap. This is what we have regarding this particular path for us. Okay, and furthermore, how can you write even dz? Dz can also be replaced as dy itself. Because of this equation, we can also replace the dz by means of dy. So I am replacing this by means of dy. Okay, now let us calculate the closed integration. The closed integration of whatever is the vector we have been given, that is nothing but b bar dot dl bar, and we have taken some contour here, indicates that whatever is the integration we are performing now, that is nothing but a closed line integration. Can we divide this into 3 open line integrations? Yes, that is nothing but L1 b bar dot dl bar plus L2 b bar dot dl bar plus integral over the path L3 b bar dot dl bar. Okay, and this can be written as what? The first thing can be written as, now if you notice, what is dl bar? In the first path, the dl bar is nothing but y cap only. So let us take only the y cap components, and the y cap component we have here is nothing but minus yz. So because of that, here it becomes equal to yz with a minus sign into what is dl bar. Dl bar is nothing but dy. So this is into dy, and for y, the value of y changes from where to where? The value of y along the L1 path changes from 0 to 1. So because of that, the integration is from the initial point to the final point. And here in this case, what do we get? Now whenever we write this, the value of z along this particular line, the value of z is nothing but 0. So because of that, whenever we write the value of z to be equal to 0, in that case the whole integration has become equal to 0. So the first integral is finally equal to 0. This is the first path integration. What about the second path integration now? That is nothing but this expression. We can write this as, this is equal to plus. Now what is dl bar along the second path now? That is nothing but z cap. So let us take only the z cap components. The z cap component is nothing but, we are having z. So because of that, this becomes equal to z into dl bar. And what is dl bar? That is nothing but dz. Okay, now along the second path, the value of z changes from where to where? The value of z changes from 0 to 1. So because of that, the initial value is nothing but 0, final value is nothing but 1. What is the integration of z dz? That is nothing but z square by 2. And whenever you substitute the limits, the answer that we will get is nothing but, this becomes equal to half. Okay, and what about the last integration now? The last integration is a bit trickier now, because we are having 2 components in case of dl bar, and in this case the integration of b bar dot dl bar. Now here we are having y cap as well as z cap components. And what is y cap component? Y cap component is nothing but minus yz. So this is minus yz, and minus yz into, we are having dy here into dy, and here we are having xz into dy. So plus xz into dy. So we have converted this particular integral into one single variable, and what is that variable now? That variable is nothing but y. But apart from that, we are also having x as well as z components. We know that the value of x becomes equal to what? The value of x is nothing but 1. And what about the value of z? Now along this particular path, if you notice, the value of z is equal to y. So wherever we have z, we can replace this by y. So this is replaced by y. So finally, what is the integration we have? That is nothing but y minus y square into dy. So this becomes equal to y minus y square into dy. Now along this particular path, starting from this initial point to this final point, what is the value of y now? The y changes from the initial point. At the initial point, the value of y is nothing but 1. At the final point, the value of y is equal to 0. So because of that, the lower limit is nothing but 1, upper limit becomes equal to 0. Please understand, from the initial to the final, initial value, the value of y is 1, the value of y is 1, final point, the value of y is 0. So because of that, upper limit, the value of y is 0. And whenever you perform this integration, what do you get now? Now this becomes equal to integration of y is y square by 2. So the first expression becomes equal to y square by 2 minus the second integration becomes equal to y cube by 3. So this is y cube by 3. Substitute the upper limit, we will get the answer as 0, and substitute the lower limit, what will you get now? That becomes equal to finally minus 1 by 2, minus of minus, which is nothing but plus 1 by 3. And whenever you take the LCM here, we will get the answer as nothing but this is minus 1 by 6. So this is the result of the third integral. Okay. So finally, what is the answer? For the first path, we are having the answer as nothing but 0. For the second path, we are having the answer as half. And for the third path, we are having the answer as minus 1 by 6. And finally, the answer becomes equal to 1 by 3. So along the closed path that has been given to us, the line integral becomes equal to 1/3. Okay.